All right, so these problems have us combining pretty much everything we've learned in this unit. So we're working with solution stoichiometry here, using concentrations. We're working with limiting reactant problems, and then we're also going back and reviewing how to write chemical reactions. All right, so I've got 2 practice problems here. Let's jump into it. It tells me that sodium hydroxide is added to copper 2 sulfate. So I have to write out my chemical reaction here. So I know I have sodium hydroxide, so that's NaOH. Okay. And I also know that I have copper 2 sulfate, so I've got to cross my charges. So copper has a 2+ charge. Sulfate has a 2- charge. So when I cross my charges properly, the charges actually cancel, and I end up with just copper sulfate. All right. Now, this is a double replacement reaction, so I have to switch partners. Sodium will become partners with sulfate. Remember, outies and innies. So sodium will become a new partner with sulfate. Sulfate has a 2- charge. Sodium is +1. So when I cross my charges, that gives me Na2SO4. And then I have to cross the charges of copper and hydroxide. Copper, I know, has a 2+ charge, and hydroxide has a 1- charge. So the formula for this is going to be CuOH2. Then the last thing that I need to do is I need to balance. All right, so I've got 2 hydroxides here. I'm going to put a 2 in front of sodium. That gives me 2 sodiums. 2 sodiums unbalanced, 1 sulfate, 1 sulfate, 1 copper, and I am balanced. Now comes the hard part. Notice, I know the amount of one of my reactants, and I know the amount of my other reactant, and it is asking me how many grams of copper 2 hydroxide will precipitate, how much of this product will form. So I know this is a limiting reactant because I'm given 2 different amounts of my reactants. So I'm going to start with the sodium hydroxide first. Okay, this is a beautiful problem. It literally includes everything we've talked about in this unit. Sorry for nerding out on you. All right, so I'm going to start with my given because I'm going to use my concentration as a conversion factor. So I'm going to start with 25.0 milliliters, and I'm going to first get into liters. Okay, so I'm going to put milliliters on the bottom and liters up top. I'm now in liters, and I can easily get into moles of sodium hydroxide by using my concentration as a conversion factor. So I'm now in moles of sodium hydroxide. Awesome, wonderful. However, I want to be in grams of copper hydroxide. That is my goal. So I'm going to get out of moles of sodium hydroxide by putting it on the bottom. And I'm going to first get into moles of copper hydroxide by putting it up top. So moles of copper hydroxide up top. That's wonderful. That was a beautiful stoichiometry. However, I am not in grams yet, which is what I want to be in. So I'm going to get out of moles of copper hydroxide by putting it on the bottom. And I'm going to get into grams of copper hydroxide by putting it up top. All right. And I'm done. So let me plug in all my values. So I know 1 milliliter has a volume of 10 to the -3 liters. If you just wanted to do this part in your head, that's totally fine. I know that the concentration of sodium hydroxide is 0.350 moles for every 1 liter. The mole to mole ratio I get for my balanced reaction, the coefficient in front of copper hydroxide is a 1, in front of sodium hydroxide is a 2, and then I need to calculate my molar mass of copper hydroxide here. So the molar mass of copper is 63.546. All right. The molar mass of oxygen is 15.999, but I need to multiply that by 2. And then the same thing for hydrogen, multiply its molar mass by 2, and the molar mass I get for the entire compound is 97.56 grams. And that's for every 1 mole. All right. So I'm going to take my 25, I'm going to multiply that by 10 to the -3rd, then I'm going to multiply by 0.35, divide by 2, and then multiply by my molar mass of 97.56, and the value that I get. And keep in mind, I have 3 sig figs here, 3 sig figs here for my concentration, so I want 3 sig figs. The unrounded value I get is 0.4268, so the 8 will round the 6 up, and that will end up giving me 0.427 grams. Well, that's wonderful, and I actually see in the question that that's my answer, but I can't stop there because I need to confirm that this, my sodium hydroxide, is my limiting reactant and not my copper sulfate. So I'm going to do the exact same steps, but now use the amounts for the copper sulfate, which is my other reactant. So I have 45.0 mils of my copper sulfate. I'm going to get out of mils into liters. All right, they're 10 to the negative third liters in 1 mil, just like I did up above. Here I need to put the concentration of my copper sulfate, right, because it's moles per liter. I'm getting into moles just like I did here. So I'm going to put copper sulfate here, just make sure it's clear I'm in moles of copper sulfate. The concentration here is 0.125. That's moles for every 1 liter. Now I'm in moles of copper sulfate, which is great, but I don't want to be in moles of copper sulfate. I want to be in, eventually, grams of copper hydroxide. So I'm going to go and put copper sulfate moles on bottom, moles of copper hydroxide on top now. Okay. So looking at my balanced reaction, this is going to be a 1 and a 1 coefficient. And then finally, my last step is to get out of moles and into grams. Now the cool thing is I've actually already determined the molar mass of copper hydroxide, so I don't need to calculate it. It is 97.56 grams for every 1 mole. So I'm going to take 45, multiply that by 10 to the negative third. Then I'm going to multiply that by 0.125, which is the concentration, and then multiply by the molar mass. And I get 0.5487. I want 3 sig figs again. So this is going to round to 0.549 grams. Now I know for sure that my limiting reactant is in fact sodium hydroxide because it only produced 0.427 grams of my product, while the copper sulfate is my excess reactant because it produced it could produce 0.549 grams. So this here is my theoretical yield, right, produced by my limiting reactant, while this is my excess reactant. All right, let's look at one more problem. All right, here it tells me 3.2 grams of potassium iodide, that's one reactant, are combined with 20 mils of 0.530 molar lead nitrate. There's my other reactant. All right, how many grams of lead 2 iodide will precipitate? Well, before I do anything, I need to write out my chemical reaction. So potassium is my first reactant. It has a +1 charge. Iodine is -1, so that's going to be Ki. That is going to react with lead 2 nitrate. So lead, I know, has a 2+ charge. Nitrate has a 1- charge. Okay, so the formula for this will be Pb in parentheses NO3 2. This is a double replacement reaction again. So innies and outies. So potassium has a +1 charge, right? It's going to combine with nitrate, which has a -1 charge. So that will be KNO3. All right. And then lead is going to combine with iodide. Lead has a 2+ charge. Iodide has a 1- charge. So that will be PbI2. All right. To balance, I've got 2 iodides here. I see immediately, so I'm going to put a 2 here. That gives me 2 potassiums here. So I'm going to put a 2 here. I've got 2 nitrates, 1 lead, and I am balanced. Now, I know, again, this is a limiting reactant problem because I'm given the amount of both of my reactants and asked how much product will that form. So I'm going to start with the potassium iodide. So I've got 3.2 grams of potassium iodide, okay? And I need to get into grams of lead iodide. Sorry, that's going to trip me up. So I'm going to put grams of potassium iodide on the bottom and moles of potassium iodide on top. I'm now in moles of potassium iodide, which lets me then use the mole to mole ratio to get into terms of lead iodide. So I'm going to put moles of potassium iodide on the bottom, moles of lead iodide on the top. But I don't want to stay in moles of lead iodide because I want grams of lead iodide. So I'm going to put moles of it on bottom. And my last step is to get into grams of it on top. So for gram to mole, I need to know the molar mass of potassium iodide. So potassium is 39.098 plus the molar mass of iodide, which is 126.904, and I get 166.022. Okay, so that is the molar mass of potassium iodide with 1. Then the mole to mole ratio here, the coefficient in front of lead iodide is 1, in front of potassium iodide is 2, and then I need to know the molar mass of lead iodide. So lead is 207.2. Iodide is, as I noted, 126.904, but I've got 2 of them, so multiply that by 2. And so the molar mass of lead iodide I get here is 461.008 grams for every 1 mole. So I'm going to take 3.2, divide by the molar mass, 166.002, divide by 2, and then multiply by the molar mass of lead iodide. Keep in mind, 3.2 has 2 significant figures, so I want 2 sig figs for this mass here. I get 4.4433, so that's just going to round to 4.4 grams. Okay, so that's my first option. Okay. For the second one, my second reactant, I've got lead nitrate. So I know the volume here is 20 mils. I'm going to actually just, instead of showing the conversion, I'm going to just move my decimal 1, 2, 3 places. So what that gives me here is 0.0200 liters is the volume of my lead nitrate. Okay, so for here, instead of using my molar mass like I did for potassium iodide, I'm already in liters. Okay, and I'm given the concentration. So notice one of my reactants is a solid, one of them is a solution. All right, so I get mixed up the problems on you. So here I'm going to use my concentration, so moles over liters, in order to determine the moles of my lead nitrate that I have. Okay, so I'm going to put that there. Okay, I'm going to get out of moles of lead nitrate by putting it on the bottom. And I'm going to put moles of lead iodide on the top. And then I'm going to put moles of lead iodide on the bottom, and then grams up top, because that's what I'm trying to get into. All right, the concentration of lead nitrate is 0.530. So that many moles for every 1 liter. The mole to mole ratio here is 1 to 1 because those are the coefficients. And then the molar mass I already got was 461.008. All right, so I'm going to take 0.02 times the concentration, 0.530, and then multiply by the molar mass, 461.008, and I get 4.8866. Notice here 20.0 has 3 sig figs, 0.530 has 3 sig figs, so my final answer should have 3 sig figs, so that will be 4.89 grams. All right, so which is actually produced? The 4.4 grams. Okay. Now, I originally got 4.5 grams. That might just be a rounding issue as far as the molar masses are concerned. That could have contributed to it. So 4.4 or 4.5 is perfectly fine. That tells me that potassium iodide is my limiting reactant, while lead nitrate is my excess reactant. All right, so 4.4 grams are produced. So these were both really awesome problems, if I do say so myself, because it really forces you to use everything we've learned so far in this unit, especially this problem, figuring out how much of a product a solid reactant will form and how much of a product an aqueous reactant will form when they are allowed to react together.